Okay, so hi everyone. Welcome to another session of the network seminar series hosted by the Center for Network Intelligence at the EC and RBCCPS IAC. It's my pleasure to introduce today's speaker, Professor Tarun Mangla. He will be speaking on understanding performance of internet video using network measurement data. Tarun Mangla is an assistant professor in the Department of Computer Science at IIT Delhi. His research focuses on using data-driven methods to understand and improve internet performance and accessibility. He completed his PhD at Georgia Tech in 2020 and then spent 3 years as a postdoctoral scholar at the University of Chicago. He earned his bachelor's degree from IIT Delhi in 2014. Professor Tarun is a recipient of Best Paper Award at IFIP TME 2018. We request the audience to keep your microphone silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them in the chat box and we will relay your questions. Over to you, Professor.
All right, let me share my screen again. Okay, I'm assuming my screen is visible.
Yes, yes.
Okay, great. Yeah, so first of all, thanks for inviting me to this talk. So when I told my wife that I'll be giving a talk at ISC, she was even more excited than me because she was an alum at ISC. And then she was like, "Hey, you should go there and you should present." But nevertheless, I mean, it's middle of the semester, hard to travel. But and again, like, feel free to interrupt me if you have any questions. I mean, the more interactive it is, I think it'll be more fun for me as well. It's 5 p.m., so I'm sure, like, I think people are a little tired. So feel free to, keep it, more interactive and all of those things, right? So by the way, I've also given a version of this talk, last year when I visited ISC. I was visiting the CSA department. So I mean, if there's somebody who attended that talk, maybe, the first portion of the talk would be similar. So yeah, apologies for that. But okay, so let me start. So this talk is about how you can enable network operators to understand performance of video delivered over the internet. So let me start by some motivation. So video is the killer application over the internet, right? So I mean, beyond entertainment over, say, using YouTube or Instagram, right? Video is also used for things like remote education, remote work, telehealth, right? It's also an interesting application from a network standpoint. It is the largest contributor to the internet traffic. So here's a graph from Ericsson Mobility, which showed that video contributed to 90 exabytes, which amounts to 71% of the total internet traffic in the year 2022, and this is expected to grow both in absolute and relative numbers, right? So naturally, given this large contribution of video in the internet traffic share, each network that is responsible for delivering the video over internet would is interested in understanding and improving video performance, right? So let's look at maybe who the networks in this video delivery ecosystem are, right? So typically, let's say as a user, when I want to watch a video over the internet. For now, let's assume you're watching your favorite, a series, maybe House of the Dragon or Lord of the Rings, right? You would connect to the content provider through your ISP's network connection, right? There could be other networks in this path. There could be some transit ISPs and all. Generally, due to flattening of internet, the number of network operators in this path have reduced, right? But nevertheless, so you see this ISP, your consumer ISP, think of it as your Reliance or Airtel. It's one of the most, I mean, this ISP is sort of common across all streaming sessions, right? And it's sort of an important stakeholder in the video delivery ecosystem, right? In fact, if there are any video performance issues, people often tend to also blame the ISP beyond the content provider. So here's a survey that asks users, how likely are you to blame different entities, including content provider, Wi-Fi, and the ISP. And you can see that ISPs often get blamed, a lot of times for video performance issues, right? So naturally, the ISPs would want to, have an in-depth understanding of the video performance so that they can optimize their networks for video delivery, right? So understanding how the video is being streamed, what is its performance, can help them in both short term as well as long term network management, right? But turns out, inferring this video performance is challenging for ISPs, right? So unlike content providers who own both the server as well as the player at the client side, ISPs do not have access to any of the endpoints, right? All they have access to are the network bytes that they send from client to server and back, right? So they are constrained to use this network uh, data that they're basically transmitting across the network to infer the streaming application performance, right? Or sorry, video performance, right? Um, and to add to that, the an increasing amount of video is now end-to-end encrypted, which means that the amount of information that ISPs have is even more limited, right? So traditionally, you could have access to HTTP headers, but it's been a while, and you don't. I mean, the HTTP headers are generally encrypted, right? So all you have access to, for example, in case of streaming, are only IP and TCP headers, right? So network operators are constrained to rely on this limited view of network measurement data to estimate QoE, right? And this is where sort of my work has been, is to sort of facilitate these network operators to understand video QoE by designing some algorithms that use basically passive network measurements, and estimate video performance. So here's how the talk will be. So first, I'll talk about a method for inferring performance of video streaming. So things like, I mean, applications like Hulu or Hotstar, Netflix, YouTube, right? And then I'll talk about a method which enables operators to infer video conferencing performance for such as for applications like Zoom, right? Or Teams or Google Meet, right? And then towards the end, I'll just give you an overview of the other kinds of things that I've been doing in my lab. Um, um, Sounds good. So I'll start with the first part, that is inferring video streaming performance for ISPs. So we'll just give you some background on how video streaming works. So most video streaming today is streamed using a protocol called HTTP adaptive streaming. I'll talk about how it works, but essentially for this kind of streaming, the performance metrics are as follows, right? Video performance is usually reflected by these metrics. First is the average bitrate, which generally reflects the video quality. Then is the rebuffering ratio. I mean, think of that, stall sign appearing, when the video is frozen, right? So how long or what proportion of the time the video has stalled, that is reflected in rebuffering ratio. And then sometimes, I mean, there's bitrate adaptation going on. The client is trying to switch the video quality based on its understanding of the network bandwidth. So frequent bitrate switches are also bad. So that sort of reflects the user experience. And then there's startup time. How long does it take to begin playing the video, right? So essentially, we are interested in inferring these objective metrics from passive network measurements. So let me now tell you how exactly HTTP adaptive streaming works, right? So in HTTP adaptive streaming, the video, think of, say, again, like maybe a Game of Thrones episode, the 1 hour long episode would be divided into chunks, maybe a chunks of 4 seconds. And then each of this chunk is encoded at multiple quality levels and stored on a standard HTTP server, maybe inside a CDN network, and all the intelligence to stream the video is at the player, right? So the player basically download these chunks one by sending the HTTP GET request, right? So for instance, the player could say, I want the first chunk at low quality, right? So it will send a GET request, will receive a response from the server, right? Once it is downloaded the first chunk, it'll download the second chunk, right? Again, maybe it is still downloading that chunk at low quality, right? So it'll send another GET request, we'll get a response, and so on, right? So now our goal is basically to infer the performance metrics that I described before for HAS, like has kind of video, right? Using passive network measurements, right? So let's look at what could be, the design of an approach that allows you to do that look like, right? So when we were designing this approach, we were doing this for a network operator which had limited access to any sort of ground truth video performance data, right? So remember, again, network operators do not have access to endpoints, right? So we were thinking, can you actually design a session modeling approach? So what do we mean by session modeling approach is that can I look at can I use the network properties of the streaming protocol to model a video session? So just I'll give you an example. So consider a hypothetical scenario where there is a content provider which is streaming a video encoded at 1 Mbps. There's only one quality, that is a constant bitrate encoded video at 1 Mbps, right? So clearly for this kind of video, the only thing that really matters is the rebuffering, right? The average bitrate is fixed. There are no bitrate switches and so on, right? And you can easily track rebuffering by just logging how much data has been downloaded on the network, right? So you do see, right? So you can easily model, given some knowledge of what the streaming protocol is, you can model the video session by just logging the data downloaded on the network, right? So essentially now the question that we were trying to answer was, can you use this kind of approach for HTTP adaptive streaming, right? So for this, we designed an approach called eMIMIC. And the key idea of eMIMIC was that it basically models a video session as a sequence of video chunk downloads, right? So if you remember how HAS streaming works, you're basically downloading one chunk at a time, and the session is nothing but a sequence of chunk downloads, right? Now the idea here is that if you can track those chunk downloads by logging the packet traces, you can essentially model how the session is evolving at the client side, and then try to estimate different kinds of performance metrics, right? But tracking these video chunk downloads using packet traces has several challenges. The first challenge is that, remember, this is encrypted video, right? So there, in the packets, there's no notion of HTTP transactions, right? So if you recall, networking 101, when the traffic is encrypted, you are basically, all you have access to is maybe the TLS transactions, right? Which may have multiple HTTP transactions in it, right? So for an operator, the first challenge is essentially, how do you isolate individual HTTP transactions, right? Because some of these transactions correspond to video channel downloads, right? So that's the first challenge. The second challenge is, once assuming you have a sequence of transactions corresponding to a session, some of these transactions can correspond to audio, others can correspond to metadata, while the relevant transactions for us are the video transactions, right? So how do you isolate video transactions from the rest of these transactions, right? And once you do that, the third is basically, how do you estimate the quality of the video chunks, right? Assuming you have isolated the video transactions, how do you estimate the video quality? Because that is needed to estimate things like average bitrate and bitrate switches and so on, right? So this work, basically, we show how you can address each of these challenges. So I'll give you an overview of that. So for reconstructing HTTP transactions, we basically use the directionality property of an HTTP transaction, in the sense that if you think of an HTTP transaction, it consists of a GET request followed by response, right? So GET request is an upstream data, right? And then the response is downstream data, right? So essentially you can look at upstream data to identify the boundaries of HTTP transactions, right? So and the downstream data can be used to calculate the volume of data downloaded for a particular HTTP transaction, right? So this is the property that we use to reconstruct HTTP transactions using packet level traces, right? Um, Now, after we do this, we basically have a sequence of HTTP transactions, and then the next challenge is we need to isolate video transactions from from within these HTTP transactions, right? And there again, we use a simple idea that if you look at different media types, they have different size distributions, right? So here's this plot illustrating that point. So if you look at the metadata, right? So metadata is usually consisting of text, right? So it's generally very small in size, right? And then if you look at audio, audio is usually constant bitrate encoded. It's not only small, but also has a very fixed size, right? So the audio chunks are typically, a fixed size. And then if you can now isolate both metadata and audio, the remaining transactions you could classify as video, right? So that is the intuition we use here to identify video transactions. But if you still, notice carefully, some of the video transactions, they have, sizes overlapping with audio transactions. Now, to avoid misclassifying these transactions as audio, we also use another insight that the duration of audio and video content that you download would be similar, right? Because the audio has to be played in sync with the video. So let's say if you download 16 seconds of video, you would not have downloaded, maybe, 1 minute of audio. You would maybe have downloaded 20 seconds of audio or 24 seconds of audio, right? So we also track the audio and video buffer that has been, that has been downloaded, and use it to sort of avoid misclassifying, if at all, some of the video chunks into audio. Okay, once we do this, now we have basically sequence of video transactions corresponding to a session. Now the idea is we want to estimate the quality levels of these uh, video transactions, right? Remember, the video is generally encoded into discrete predefined quality levels, right? And these are usually characterized by some average bit rate. Most content providers use variable bitrate encoding. So an individual chunk may have different size, but on an average, it will have some predefined size, right? So here's this plot that is illustrating it. Right. So on the x-axis are the different quality levels, and y-axis correspond to the chunk sizes, right? Now, a simple idea is you can use the chunk size to estimate its quality level, right? But given that this is variable bitrate encoded data, this is not enough, because you can see that um, you know the chunk size maybe, they're overlapping across bitrate levels, right? Especially with the neighboring bitrate levels, right? So we also use another insight, right? That content that, a video player would not um, erratically switch the video quality, right? Because too many switches are also bad for user performance, right? Typically, a video player would only switch the quality if the network conditions have changed, right? So that's how bitrate adaptation works, right? So we also log for each, video transaction. We also log the network throughput that is observed for that transaction, and then basically we use a simple heuristic that any change in quality has to be accompanied by a change in chunk throughput, right? So this lets us, separate chunk, sort of identify chunk uh, quality level changes without sort of confusing with changes due to variable bitrate encoding, right? So once we do that, we basically have a sequence of video chunk downloads, as well as their quality levels and timestamps, right? So once we do that, basically now we essentially can model the video session, right? So the average bit rate, or the average video quality, is simply the average of the qualities of the chunks that we have seen so far. Bitrate switches are also easy to calculate. You can just look at, consecutive um, chunks and see if the quality has changed. and for calculating rebuffering ratio, we simply use this. We simply model the buffer occupancy at the client, right? We assume we know how long a chunk is, and that is usually fixed for each content provider. For example, Netflix might be using a 4-second chunk. Disney Hotstar might be using maybe a 3-second chunk, or right, and so on, right? So essentially, whenever you download a chunk, the video buffer, it sort of increases by the duration of the chunk, right? But at the same time, the video content is being played on the screen, right? And assuming there's linear playback, that is, you're only playing 1 second of data in 1 second, you can essentially track the buffer draining, and you can also track how the buffer is getting filled, and then you can basically also track if there's any time where the buffer was empty and how long it was empty, and use that to calculate rebuffering ratio, right? Um, I'll stop here if there are any questions. Okay. So all right. So now how do we evaluate this algorithm? So we basically had an in-lab setup where we emulated different network conditions, and basically streamed sessions from two popular streaming services. In the paper, we refer to them as VOD1 and VOD2. This was just because this work was done in collaboration with AT&T, the telecom operator in the US, and it had a sort of a confidentiality policy, right? So we were not allowed to disclose the streaming service names, but essentially these are these two popular streaming services, and we collect both the ground truth, performance metrics, as well as the network data corresponding to the sessions, right? So I'll just show you one result, that is the estimation accuracy of free buffering ratio. Just to put the numbers in perspective, we had also implemented at that time what was a state-of-the-art approach, which basically classified rebuffering ratio into 0, mild, and high using machine learning. And here's the confusion metrics comparing eMIMIC with the ML baseline, right? The numbers are, I mean, this is a confusion matrix, right? The rows represent the actual values, and the columns is the predicted, right? And the entries on diagonal should be higher, right? So you can see we can predict both 0 and high rebuffering ratio sessions with higher accuracy compared to the ML baseline, right? So this was, I mean, summary. I mean, this was one of the approaches that we have developed for, inferring performance of encrypted video streaming traffic. There have been other works that I've done in this domain, in which mostly look at the system level challenges. Let's say if you have to deploy this approach in a large scale network, what are the system level challenges? We've shown a design of a system, that can be used to infer, video quality of experience or video performance in a cellular network. And we've also characterized performance for different popular streaming services. So this system is actually deployed at AT&T. And then we've also looked at other constraints. That is, maybe for an operator, getting packet level data at scale is very challenging. So can you use some coarse grained data which is more readily available for inference? So there we used a machine learning based approach. There are also some open problems that I'm interested in looking at in this domain. One is, there have been newer video streaming formats, including virtual reality, which are both characterized by slightly different streaming protocols, but also the application performance metrics are also different, right? And now, can we design methods that let network operators infer these performance metrics for these newer streaming formats? Then the other is that is more sort of how do you sustain, if you build something, can you sustain it over time? So as naturally applications tend to evolve, both network protocols, encoding standards, and all of those things evolve. So can you design a continual validation framework that automatically sort of detect these changes and sort of adapts the inference algorithms to sort of account for these changes. So these are a couple of problems that I'm sort of looking particularly in the video streaming domain. Okay, so the next, with this, I'll end this the first portion of the talk. Let me know if there are any questions, or otherwise I'll go ahead. Okay, so the next part, I'll describe another algorithm that allows operators to infer performance of video conferencing. So think of the Zoom session that we are currently logged on, right? Um, so just want to highlight that video conferencing and streaming are two different applications, right? Although they're both delivering video over the internet, but in terms of the architecture, they're different, right? So video streaming is a client server application. Video conferencing is more like a peer-to-peer application. And also, because of the nature of the applications, the performance metrics are also different between video streaming and conferencing, as well as the application and the transport layer protocols that you use are also different, right? So naturally, the algorithms that you design for video streaming would not work for video conferencing, right? So you need newer methods to infer video conferencing performance. So let me define the problem scope for video conferencing more precisely. So we essentially want to figure out or infer the following uh, performance metric. So one is frame rate, that is how many frames you're sending per second. The bit rate, frame jitter, what is the inter-arrival time variation of frames, and what is the resolution of the video that you're sending your frames at, right? And what is available to us that will allow us to estimate these performance metrics. So video conferencing applications, they typically use a protocol called real-time transport protocol, or RTP. That is an application layer protocol, and it runs over UDP as its transport protocol, right? So traditionally, RTP headers are unencrypted, and can be used to infer a lot of these metrics, right? But more recently, an increasing amount of these service conferencing are either encrypting these RTP headers for privacy reasons, or they're using custom protocols, custom proprietary protocols, for which you do not know the format of the headers anymore, right? For instance, Zoom uses a custom RTP protocol, and there was in fact an INC paper which was essentially around coming up with some methods on how to infer the structure of this custom proprietary protocol, right? So we take a different approach now. We consider this constraint that the RTP headers may not be available all the time. So can you use this more readily available IP UDP headers to estimate video conferencing performance metrics, right? So that is the problem that we set up for ourselves. And then, of course, now how to go about it. So again, we thought, okay, like we were able to design a session modeling approach for video streaming. Can we use session modeling here as well in video conferencing? So the idea is basically, if you think of a video conferencing session, it's nothing but a sequence of frame downloads, right? If you remember, video streaming session was a sequence of video chunk downloads. Here, a video conferencing session, since it's real-time encoded, you basically encode a frame and you send it on the network as soon as possible. So you can basically think of a conferencing session as a sequence of video frames, right? So if you can track these frames in the packet traces, you can essentially infer a lot of the metrics that I described earlier, right? But the challenge really is how do you detect video frames from IP UDP headers, right? If you remember, right, UDP header is only an 8-byte header and does not really have information about frames, right? And so is IP header, right? So how do you detect this, right? So here again, we use an insight that the inter-packet size difference uh, is basically can be used to detect these frame boundaries. And the reason is because if you think of a video frame, a single video frame, when it is packetized, right, when it's converted into multiple packets, um, now you can split the data across packets in any which way you want, right? But typically these services or these conferencing applications, they packetize the video frame into equal sized packets, and there are reasons to do that, particularly to support, for example, forward error correction in a more efficient way. It makes sense to do split a video frame into equal sized packets, right? So here's a plot that also empirically shows that here we look at both intra-frame packet size difference as well as inter-frame packet size difference, right? And you can see that the intra-frame packets are size difference is very low, right? It almost is less than 2 bytes for most of the packets. Only a very small proportion of packets have a difference greater than 2, right? And whereas the inter-frame packet size difference is larger. It's because of natural variations in conferencing data, right? One frame is different from the next frame because of encoding, the scene variations, and all of that, and that leads to variations in packet sizes for that for those frames, right? um, right. So here's a sketch of, if you were to design a session modeling approach for frame rate estimation. So basically the idea is you have IP UDP packets. What you really have is basically for each of those packets, you know their timestamp, the length of those packets, as well as some IP headers, right? Of course, I mean, these packets can have both audio and video data, and we use a similar approach to identify video from audio, that audio packets are generally smaller in size. So anything that was less than 300 bytes, we 306 bytes, we classified it as audio, and rest was classified as video. And this was fairly accurate. Um, Now then we sort of grouped these packets into frames based on the size difference across packets. And once you do that, you can now essentially calculate frame rate by looking at the number of frames that you observe in 1 second window, right? So that is your number of frames per second, right? So right, very simple approach, right? But turns out this method has several limitations, right? There are cases where it fails. So I'll just explain one case. For, as I mentioned, right, in general, the inter frame packet size differences are larger, but this is not set in stone, right? For whatever reasons, I mean, this is all random, right? So you might have two frames, two consecutive frames have almost that have the same size, right? So what will happen in that case, if you're using inter-packet size difference to identify frame boundaries, you'll basically end up combining these two frames, as you'll think of them as single frame, right? There are other cases where also, this approach would not work. I'll not go into that, but basically cases where there's network jitter, where packets get sort of reordered, you'll see basically that will lead to issues, right? Because UDP has no notion of sequence numbers, so there's no notion of ordering of packets within IP UDP headers, right? So if there's packet reordering in the network, your whole idea of using unique packet sizes will not work, right? So you'll end up splitting packets, interleaving. So you'll end up splitting frames. You'll end up interleaving frames and so on, right? And it's hard to design a heuristic that will solve things for all of these cases. Although we tried to do that and it did not work, right? So then we thought, can you, instead of just looking at one signal, that is the inter packet size difference, can you look at multiple signals, and maybe look at them using a data driven approach? So maybe that will give you better results, right? So essentially then we applied machine learning to this problem. So we basically define two category of features. The first category of features were features that really came from domain knowledge. Essentially number of unique packet sizes. Um, Remember, because that how you packetize a frame, it will lead to some interesting patterns of packet sizes, right? And then we also defined another feature, which is number of microbursts, is like how many packets are sort of spaced together in the network, right? And this is useful because typically a frame is sent as soon as it is encoded on the network, right? So essentially now, if you're delivering video frame by frame, and maybe each frame has a difference of 1 by 30 seconds, right? If it's 30 FPS video, then you essentially have burst of packets on the network, right? So if you can track these bursts, you may be able to track the frame rate, right? So that was the intuition of define using number of microbursts. And then the second category of features that we used was standard flow level features that people have used for different kinds of ML tasks. So things like, your bytes per second, packets per second, packet statistics on packet sizes, inter-arrival times, and so on, right? And essentially we posed it as a supervised machine learning problem. The idea is that you collect these features for one time window, and for that time window, you also have the corresponding ground truth performance metrics. You train a supervised machine learning model, and then use it to predict the performance metrics in the real world, right? So that is what we did. So we trained four different, for example, random forest models to predict FPS, bitrate, jitter, and resolution respectively. So here's how we validate this. So one part of the validation was very similar to eMIMIC, where we essentially had in-lab setup, which we basically had multiple video conferencing calls, and logged both the network metrics as well as the application layer metrics, right? And then the other set of data which we obtained was from real world clients. So we basically had deployed Raspberry Pis inside people's homes. So this work was done when I was a postdoc at Chicago. So we had basically Raspberry Pis deployed in around 50 homes, and then we had these Raspberry Pis conduct a video conferencing call with the university server, and then we logged both the network traces and the corresponding performance metrics. So here's the frame rate estimation accuracy. So we evaluated our method for three different video conferencing applications. That is Google Meet, Microsoft Teams, and Cisco WebEx. So y-axis is the error in estimating frames per second. So the IP-UDP ML is really the method that we want to test, evaluate. And then we had several baselines that we also use to contextualize the error, right? So the two baselines, RTP-ML and RTP-heuristic, essentially used application layer headers as well, right? Remember, here we are using only IP-UDP headers, but then we also had baselines which use more information, and they should naturally be, have higher accuracy. And then this is the IP-UDP heuristic is the heuristic I told you about, right? Which was basically using the difference in interpacket size, right? So I want you to look at the results for Teams, for instance, right? So this is a box plot. The tighter this box plot is, the better, and the tighter it is and the closer it is to zero, the better the method is, right? And then the numbers on box plots, they represent the mean absolute error. So if you can see, right, the errors of IP-UDP-ML, they're comparable to the both the RTP heuristic and RTP-ML, right? The RTP heuristic and RTP-ML, right? So we get reasonable accuracy in predicting frame rate. And then we also looked at which features are important. So here's, for example, for predicting frame rate particularly, right? It's now, I mean, it's sort of intuitive, but essentially this semantic feature, which was essentially based on the knowledge of how conferencing works, that is the number of unique sizes, was the most important feature. Similarly, for bitrate, bitrate is essentially calculating the number of bits that have been transmitted. So number of bytes was in fact the most important feature. So what we found was, for different metrics, we had both semantic level and network or flow level features that that came out to be the most important features. Okay, just to summarize this work, the work is basically trying to estimate um, performance metrics for video conferencing. And what we found was that designing static heuristics was more challenging here compared to video streaming. But a simple ML model that uses bunch of signals, including both semantic signals as well as some general network level signals around throughput and packet inter-arrival, etc. They give comparable accuracy to using RTP headers. There's some open problems. Is essentially, so most of the evaluation here was done using web-based clients. We have not looked at the accuracy of our approach using native clients or non-web RTC clients. Then we have not looked at different kinds of application modalities, right? For example, if I'm now actually there are multiple people in this call, there's screen sharing going on. Can you actually estimate, performance metrics for these kinds of scenarios, which will basically show up as different kinds of data for a network operator, right? And then how do you develop methods that are scalable, that will give you real-time inference? So there's some system level challenges if you try to design those methods. So those are all open problems that I'm interested in looking at. Okay. I'll stop here if there are any questions. So we've covered two. Yeah. So
yeah, one question. So, especially for the video conferencing part, I believe there would be separate substreams to deal with the screen sharing and video as well as, I don't know about the audio,
yeah,
and probably the control plane as well. So how
yeah.
do you differentiate these substreams? Because it could be possible that the screen sharing would have similar packet size distributions.
Yeah. So actually we haven't looked at that part, right? So the work was mostly about a two-party conferencing call. But you're right. So these different modalities, they pose their own challenges. So if you're just using IP UDP headers, in fact, all of these substreams, they would appear as they would appear as within the same 5 tuple, right? So it's not like you can use the 5 tuple to separate these substreams. So in my mind, I think the only sort of signal here you have is really the inter-arrival times and sizes of packets that you're seeing to sort of somehow identify. Maybe you don't necessarily identify each of these the packets corresponding to each of these substreams, but you sort of jump one step and directly infer what is happening on each of the substream, right? Maybe the packet, like if the network conditions are bad, all streams kind of suffer, right? If that is the case, then you can maybe use flow level features to detect metrics. But again, we have not looked at any of that yet. It was partially because I mean it's a harder problem, but and also like setting up test beds for those was also a little challenging. So we did not look at that yet.
One more related question, if there's
Yeah.
time. So, have you is Quick protocol or HTTP3 used in any of these services?
So, interestingly, that's a great question. So, Quick is used not for conferencing kind of applications, because Quick has, well, I mean, you can turn off so Quick has reliability, right? And for conferencing, you don't want reliability because that can be a performance blocker, right? But typically, I mean, people have used RTP, so it's not used in context of conferencing, but it's definitely used in context of streaming, right? So in fact, I think YouTube uses Quick. Um, and we have not actually validated our approach for Quick per se, right? But the hunch is that it'll probably lead to similar. I mean, the directionality property might still remain. Quick, although allows pipelining of HTTP requests. So you can send multiple HTTP requests in parallel. Particularly, I think what we have seen is pipelining of audio and video requests on the same, same quick connection. So that might, hamper with, again, modeling based approaches. Um, uh, but we haven't, really evaluated those.
Thank you.
Yeah. Any other question? Okay, so if not, then I'll just give. I think we have maybe 5 or 6 minutes, so I'll just give a quick overview of some of the other work that is, that I've been doing, including work that I've started in the past 1 year since I've joined IIT Delhi. The overarching sort of methodology or the kind of things that I do is basically I essentially do a lot of measurements work, I specifically build, develop methods and build systems that help, different stakeholders of the internet understand, performance and accessibility of the internet, right? And so some of the work, or some of the direction that I'm particularly looking at are, one, is mapping and mitigating internet inequity. For most regions, you have good, maybe you have good internet access, but there are still areas where you don't really have good internet access. And turns out mapping that itself has some challenges. How do you get good quality data of internet performance as a policymaker, or as a local government, or as a regulator? It is not clear. The second kind of work is more, you know traditional networks work, is basically how do you enable automated network management using machine learning. And then third is the measurements for different kinds of networked applications. So just to give you some ideas about what I do here. So particularly around mapping and mitigating internet inequity, we've been so one project that we've started. This is work in collaboration with IT folks at IIT Bombay, Triple IT Delhi, and IIT Kharagpur, is around measuring cellular network performance. Particularly, we are interested in measuring 5G network performance in India. So this is both a measurement study where we want to characterize how different operators are configuring their networks, how the performance varies in, under different kinds of scenarios. Right, and of course we want to characterize, and for that we are basically right now in the process of building a system, which lets, maybe, users install apps and collect, different data at different network layers, including both physical layer as well as, higher layers in the network stack, including, application layer. So that is one study that we're currently ongoing. So you could think of it as a very macro level thing. And while doing these studies, what we've also discovered that some of the tools that are used to measure internet performance, for example, speed test. I'm sure like all of you have used speed test before. They have certain limitations. So just to mention some of the limitations, one is that they consume a lot of data, right? So if you're measuring your speed over a 1 Gbps connection, it actually ends up consuming, order of a gigabyte, or if not more, data, right? And it's particularly if you're doing it over cellular or even wired, right? This is very intrusive, right? So can you develop methods that are more lightweight? And then also once you measure speed, you're only given one number, right? You don't really know what to do with that number, right? Like who is to blame? Like, you're measuring speed. The speed is essentially against a particular test server, right? So you don't know whether the server was bad, there was an upstream network transit ISP that was bad, or was your consumer ISP bad, or is your Wi-Fi to blame, right? So adding diagnostic information to these speed tests is something else that we are looking at. So again, so just to summarize, like right from the macro, right, to measuring performance of maybe, of a network in maybe a city or maybe a university campus, to also like looking at the tools that are being used to measure performance, right? So that is the kind of things that we are looking at. Yeah. the second direction, as mentioned, was basically there's an increasing, as networks have grown, they've become more complex, right? So all of these domain knowledge-based heuristics, they may not be the best, right? So they need to sort of upgrade, right? And people have started looking at machine learning to sort of automate some of the network learning tasks, right? So if you think about it, right? So there's a lot of network data that is available nowadays, and you could, traditionally what the learning tasks were sort of solved through human intervention. Now the idea is to use machine learning to solve those learning tasks. So now the whole idea is, the kind of things that I'm working on is basically developing ML-based methods for specific learning tasks. So including, what I spoke today in context of conferencing, right? We're basically inferring performance for conferencing that will feed into this network management loop. And then from designing, methods for specific learning tasks to also thinking about designing general purpose ML pipelines. So that can, run that across different kinds of learning tasks, right? So both pipelines for data collection as well as, ML models, right? Particularly with the coming up of, these more, with deep learning models, including, these transformer based, think of, large language models. Like the idea is, can you use these models, or can you adapt maybe the foundational models that have been proposed for NLP domain to network domain, and use them for, different kinds of learning tasks. And the other set of things that I've been looking at is, measuring network dynamics of different and, modern applications, right? So particularly one application that I always find intriguing is these digital payment applications. And right, think of Paytm, Bharat Pay, Phone Pay, and there's not much actually that is known about the network dynamics of these apps. So we are conducting measurement studies, trying to understand how these apps work, how they're designed, are there improvements in design, particularly from a network standpoint that we can suggest. And then we're also looking at, streaming performance for smart TVs, right? People are, now watching over the top content on TVs, right? So how does that perform, particularly maybe on low end devices versus high end devices? Can the apps be designed in a smarter way? So those are just some specific examples, but the idea is to sort of measure network dynamics of more modern applications. So with this, I'll end my talk. I'll be happy to take more questions. I also want to say that I'm looking for PhD students. So if there are any sort of master student, or if you know of your friends who are, looking for PhD positions, please share this information. Yeah, thanks, and I can take more questions.
Thank you, Professor, for an informative talk. I
Yeah.
request the audience to feel free to ask questions if any.
Yeah, Preetham, you have a question?
Yeah. So one is, how did
Tejas.
you do the instrumentation or the measurements? Did you just mirror the traffic and collect entire packets, or did you have some switch-based, what do you like, the smart processing of packets or the pipelines inside the switch itself?
So yeah, so I think that the work that I actually have uh, talked about, they were mostly using either in lab, measurements, or measurements in real world, but at a single host. So we basically collected data either at the router, but it was not a lot of data, right? It's not like a commercial grade router, so it was easier to collect. But I guess what you're referring to is, how do you do collect data at large scale and do processing of that data, particularly if you want to maybe collect some custom headers from the network traffic, that can become a challenge. And in fact, that's what we also encountered. So when I was interning at AT&T, we designed this eMIMIC approach, and we thought, okay, we can test it out in AT&T's network. But of course, AT&T was not collecting packet traces at a large scale, right? I mean, the overhead is just too huge, right? And then the other approach is maybe you have, programmable, packet processing happening on the switches, but even that for commercial operators, it's not. I mean, it's not easy to do because they typically get equipment from vendors, and it's not easy to program, right? Yeah, so for those cases, we essentially then we switch to another approach is like, hey, let's see what is available and then just design approaches for that. But more recently, I've started developing data collection pipelines um, in on the campus network. So at IIT Delhi campus network. So there we are looking at approaches where you can essentially do real time sort of processing of packets inside a switch. So there are, I mean, multiple switches that are available that let you do that, and also in a more scalable manner. So yeah, but I mean, so all of the work that I have told you about so far hasn't actually used any sort of packet processing at this.
So have you looked at sampling-based approaches? Because S-flow like protocols are supported in almost all commercial switches.
That's a good idea. Actually, turns out, I mean, we wanted to look at those sampling based approaches. In fact, I mean, we for streaming, for example, what we thought was that sampling in one direction is still okay, like, right, and but particularly, I mean, if you're asking this question like in context of AT&T, what we found was that even that was challenging. I mean, for a commercial network operator, doing you collecting sample logs at a large scale was also, I mean, was not practical, is what we found. But you're right. I think you could potentially look at approaches which sort of which assume that there's some sampling going on, and then I think designing approaches for those kinds of network data collection scenarios would be interesting. But off late, I think that the trend is more towards doing packet processing at the switch itself using these more programmable switches. So I think that's what I mean, I'm more inclined towards these days. But yeah, I think sampling is a perfectly viable approach in case of networks where it's programming is not possible. Yeah.
I agree. Yeah. Once idea around because you already have a mechanism for estimation, it would be if to detect from at the user end whether your traffic is being throttled by the ISP. So throttling detection in the interest of net neutrality or censorship or that kind of thing.
Yeah, that makes sense. I think what you're referring to is maybe like have different clients stream maybe different kinds of content and under similar network conditions and see if there's any throttling going on. Yeah, I mean that's definitely interesting. Yeah, maybe we can chat more about that as well.
Sure. Yeah. Thank you so much.
Yeah. Um, any other question?
Okay, since there are no questions, I would like to end the meeting. Thank you, Professor, and thank you everyone for attending, and have a great evening.
Yeah, thanks for inviting. I mean, I had a great time. Yeah. Hope to, I think, connect with some of you maybe at ConsNets or other conferences, as well as, I mean, feel free to, again, like I'm saying, I'm looking for PhD students. So feel free to forward this to your friends. And if there are any master student, please don't hesitate to reach out. All right. Thanks.